Some brief reminders. Yesterday we began chapter 16, started looking at the electric fields within capacitors, talked about what a capacitor is, what its function is. Today we're going to talk about voltage, which we will continue using for a little while. Voltage is pretty important to how most modern circuits function. So as a concept, make sure that in our discussions of voltage that concept is one that, as you study, make sure that is a concept that works for you. If it doesn't, please let me know as we start discussing it. We will have lab this Thursday. We'll meet again at 11, so keep that on your schedule. After this week, we'll be back on every 2 weeks. And I think that's all the general announcements. How you guys feeling? I hope 4th of July's were nice. If no one has any questions or concerns at this particular time, then we will continue on. All right. So, make sure to be following along in the notes. Quick review. This object is commonly referred to as a capacitor, where two separate plates have been separated by a distance and electrically charged. Actually, I'm going to skip ahead just a little bit to try to show an additional picture. We'll get to this question later. Just for now, this is an additional picture kind of showing what the capacitor would physically be made out of. Two separate plates, each have their own surface area, each some distance apart. Each has some amount of electric charge on it. And because both plates are charged, there is a constant electric field between them that does not change based on how close you are to any single plate. So it's an area of constant field. And as you put a charged particle within that particular field, it's going to have a certain amount of potential energy based on where it is, kind of like how an object in a gravitational field has gravitational potential energy based on how high above the ground it is and how far it could fall. Particle in that field will then begin moving. Its potential will become kinetic energy, so its potential is going to drop as it moves from one side of the field to the other, which means that there is a difference in its potential from one side to the other. We refer to this difference in potential as voltage, when specifically speaking about difference in electrical potential. So, voltage is probably, I'm hoping it's a term that you would have heard before. It's one of those words that kind of get tossed around in the common vernacular and in sci-fi as just a word that refers to electricity. Like, you might, Back to the Future, Doc Brown might have said something about, 9,000 gigavolts or something like that. What that actually measures is the difference in potential between two parts of an electrical circuit. And charged particles always flow from high potential to low potential. They move from where they have a bunch of stored up energy to where they have less stored up energy. And it's the same way whenever something is falling. You have high potential up here, low potential at the ground, and so you just fall. You go from the area of high potential to the area of low potential. Now, there are a few different ways to calculate voltage. It is, first of all, a measurement of the change in potential between two areas. And so as a result, the first formula is the change in voltage between two locations. And again, voltage is the difference in potential between two sites. So voltage is pretty much always going to be a delta V, and it's a big uppercase V to separate it from velocity. One way to define voltage is looking at the change in potential energy between the two spots you're looking at, divided by the charge of the particular object that's going to be moving between those two spots. So you set up a capacitor, there's an electric field inside of it, and you put a charged particle on one side of the capacitor. It has a certain potential energy on that side, and it's going to lose that potential energy as it moves to the other side. That change in potential energy divided by its charge tells you the magnitude of the voltage that acts on that particular charged particle as it is moving. Excuse me. An additional version of the formula, this middle step here, is just kind of someone's work as they kind of took an in-between step. They plugged in our delta PE formula from a few slides ago, and as a result, delta V can also be equal to the electric field times the distance the particle moves within the electric field. So this would tell you the change in voltage from one point in that field to a different point in that field. Now, the idea of change in potential is probably not a way of describing things that is common to a lot of people. Unless you are a physicist, unless you're using those terms relatively often, that's not a turn of phrase that comes up all that much. So, while the word voltage is one people have heard before, the actual definition of voltage is kind of strange at times. It can feel kind of strange to some people. And so, how I like to describe voltage is basically as the electrical equivalent to water pressure. Say you're looking at a river that's flowing. All the water in the river flows downhill, downstream, from high potential to low potential. Each water molecule in the stream moves from where it has high potential up at the top down to where it has low potential at the bottom. And the water pressure is kind of the force, the mechanism that drives it down that hill, that drives it to make that change. The more water pressure that's acting on the water, the faster it's going to make those water molecules move in the stream. Voltage is very, very similar to that. Voltage is like the pressure that's driving electrons to move from one part of the circuit to the next. It's literally going to be pushing them from where they have high potential to where they have low potential so that they can keep on moving, so that they have their kinetic energy and that they can move on to the next part. It's also pretty similar to falling. So you could imagine electrons as just falling through a circuit. But voltage is like water pressure. And I'm going to kind of refer back to it in those terms pretty often as it comes up in more and more situations, because as we continue on, we're going to start talking about actual circuitry, looking at how circuits are built, the different components in them, how the electricity works within the circuit to create the effect that you want. Voltage is going to become a pretty important concept, looking at those specifically. So, potential difference, difference in electrical potential is voltage. Those are synonyms. I want to make sure that's clear. It is measured in the unit of volts. So for once, it's nice and straightforward. The unit and the variable actually kind of match. So voltage is measured in volts. The symbol for volt is a V. The symbol for voltage is V. So thankfully, it's not a weird, completely different unit this time. So, short sample question to try to get some work related to this in your notes. The potential difference between two parallel plates is 2.5 times 10 to the negative fourth volts. So that is the voltage. Oh. Well, I swear this is like the third example in these slides that I goofed up on. I apologize. The question doesn't actually give you all the information that's needed. Oy, I apologize. Okay. Give me a second. I need to change the parameters of the slide. Huh. I read that all wrong. I'm sorry. I think I had different work for a different question, and then the actual... Yeah, I did work for a separate problem completely, and the wrong image of my own math wound up on that slide. I'm sorry. Like, that's the third time in as many days. I think I need a break. Okay, so I've reframed the question so that the math for it actually makes sense. We have a capacitor, and there is a certain potential difference across the two plates. So there's a certain electrical voltage here. Say it's plugged into a circuit with a battery that provides this amount of voltage. The plates are 1 centimeter apart. What would the electric field strength be within this particular capacitor? So delta V can equal E field times delta X. So delta V equals E field times delta X. Plug in our delta V. Again, all voltages are technically delta V. Even if a formula has just normal voltage in it, there's still the implication that it's the difference in potential between two spots. So sometimes the delta might not be there, but it's always kind of implied. Plates are 1 centimeter apart. Convert that to meters, and that gives us an E field strength within the capacitor of 250 newtons per coulomb. Excuse me. Something you may have noticed about some of these formulas, and I've kind of been hand-waving past it a little bit, is the placement of negative signs that I haven't been addressing. So say here, in this particular formula, delta V can equal E field strength times delta X. There's a difference in potential in an E field as you move from one part of the field to the other. The reason that negative sign is there is because physics kind of weirdly sets up all of the formulas from the perspective of protons. All the formulas are designed such that positive direction is the direction that protons are naturally, logically going to be moving in. And the negative is there basically because electrons are always going to move in the opposite direction as protons. If you have an electric field, all the field lines move to the right. Protons will move to the right, but electrons are going to do the reverse. Because electrons don't want to be near the negative plate, they want to be near the positive plate. So a lot of the math is set out from the perspective of, well, a proton would do this, it's the positive particle, so we have to set things up as the positive, and then the negative is the exception, so it does the backwards thing. Except, I don't know why they did that, because the electrons are the particles that actually move in electricity. The electrons are what actually forms electricity. So that's the reason that they're there, and they're ultimately kind of pointless because, like, we know what direction the proton would move in, we know what direction the electron would move in. It's kind of weird to scale it from the proton's perspective if the electrons are the things that are moving most of the time. But it's possible that the physicists who were first writing these formulas a couple hundred years ago didn't actually know that electrons were the negative ones, or the ones that made electricity work. So it's kind of a relic in that regard. So, don't know why I said that. I need to take a sip of water. Capacitors are objects with two separated plates and a constant E field between them. The E field is really only constant, like, right sandwiched between them. You can see in this diagram that field lines do kind of still curl out from the sides towards the other side. But right between them is this kind of exceptional area where all the field lines all point in the same direction and they all remain the same strength. Within that constant E field, there's a difference in potential, a difference in voltage as you move from one side to the other, and the function of a capacitor is to store charges inside itself, to store charges within the E field, and to store energy within the E field. That energy is released when the charges in the E field move and exit the capacitor out the other side. For this reason, we have formulas designed to... Whoops. Back up. Simplify first. We have formulas in place to help us determine how effective a given specific capacitor is. There's different factors. If you were to try building a capacitor, which actually isn't that hard, you just need two plates separated by a distance. One side is positively charged, one side is negatively charged. That's a capacitor. And when we meet up for lab, I can demonstrate that you can do that with two pie pans and some wires, basically. Two pie pans, battery, and some wire. You can build a capacitor. How effective that capacitor is at doing its job, remember, the job of a capacitor is storing charges and storing energy in itself. How good a certain capacitor is depends on a few factors. In order to measure how good a specific capacitor is at doing its job, we have a couple of formulas in place to describe that. The measurement of how good a capacitor is at being a capacitor is called its capacitance. So what is its capacity for being a capacitor? That word is starting to lose all meaning. The C in this formula here represents the magnitude of that particular object's capacitance. How good is it at storing charges? How good is it at storing electricity? Capacitance is another new variable, and thankfully the capital C makes sense as the variable for capacitance. What's kind of frustrating is that its unit is farads, named after the scientist Faraday. You might have heard of a Faraday cage. This unit is named for the same person. So the unit of capacitance is farads. And capacitance is, like, the metric for capacitance is defined as how much charge can the capacitor hold within itself per unit voltage across it. Whenever you build a circuit, the circuit is always going to have a different voltage in it based on the battery that's driving it. A place where you may have heard the word voltage just kind of around in the English vernacular is in relation to batteries. Like someone might have a 9-volt battery, or you might have heard someone talking about their car battery in terms of the number of volts that it's able to output. Batteries supply voltage to circuits, and the battery you're using determines the voltage in the circuit. And the same capacitor could be exposed to different voltages based on what circuit it's in, based on what battery it's connected to. So the same capacitor could hold a different amount of charge based on the voltage that's currently across it. This formula exists to tell us, if you know the capacitance of a capacitor, you can find how much charge it's able to hold for a specific voltage that is across it. So you put it in a 9-volt circuit, you can figure out how much charge it can hold. If you put it in a 12-volt circuit, you can figure out how much charge it was going to hold. Again, holding charge is its job, so it's important to be able to calculate this. There is an additional formula, because this formula is kind of describes what the capacitor does within the circuit it is a part of. If it's a 1 farad capacitor, it can hold 1 joule of charge if it's plugged into a 1-volt circuit. There's a separate formula that can tell you what a capacitor is capable of independent of what kind of a circuit that it's plugged into. I mentioned a second ago that you could you could build a capacitor out of pie pans, some wire, and a battery. That is entirely possible. But there's a reason we don't really build normal capacitors you'd buy at Radio Shack out of pie pans. It's because there's better materials to build them out of. They're more effective at different sizes. So the physical components of your capacitor also affect how it's able to function. So there's a separate formula that you can use to figure out the capacitance of a capacitor that you have just constructed. Say you want to build a capacitor knowing that it's 10 farad. You then would need to build it with this formula in mind. Its capacitance is equal to this variable here, which is a fundamental universal constant. So this symbol, I think that's a lowercase sigma with a subscript 0 attached. This is the permittivity of free space. That fact is not super important. You don't have to know its name. All you need to know really is this is a constant that comes up. It is a known thing in physics. It's in a lot of the textbooks. It is a constant. It is specifically this number down here. You have access to it. It's the same as any other constant we use, except this one shows up in more than one formula. This constant is more useful, shows up frequently outside of this particular context. This isn't like the gravitational constant or Coulomb's constant that only shows up in one specific situation. So this may show up in a few other formulas from time to time, but this particular symbol refers to this specific number always, 8.85 times 10 to the negative 12. So that's the same no matter how you've built your capacitor. The factors that actually affect a capacitor's construction are, one, the surface area of its two plates, and two, how far apart the two plates are. I'm going to jump around a little bit in my slides here. I showed this image briefly a second ago, a minute or two ago. And this picture is kind of a virtual demonstration of the physical capacitor and the factors that can inform it. So here we have the two plates that are separated by some distance. One's positive, one's negative. There's an E field between them that goes from the positive side to the negative side. Each of these two plates has some surface area, which is the A part of the formula. And basically, the bigger the plates are, the physically more surface area they have, the more charges they're able to hold on to, and the more electric field that they're able to produce and send to the other side. So bigger capacitors tend to function better because they have literally more space for charges to exist in. They are able to produce more electric field. The other variable, D, is the distance between the two plates. So if the plate, notice that it's on the bottom of this fraction right here, which means that if the two plates are farther apart, if the distance between them is greater, that drives the performance of the capacitor down because it's harder for the electrons to get from one side to the other. It's a slower process. But the closer together the two plates are, the better it performs because it doesn't take as long for charges to get to one side to the other or for E field to get from one side to the other. So you can change the effectiveness of a capacitor just by changing its plate size and the distance between the two plates. And then the capacitance, the C, that you calculate here for what you constructed will go on to inform how it functions in an actual circuit, how much charge it can hold in a certain amount of voltage. When we meet up for lab, I'll show you an actual physical capacitor. I'll show you the pie pan one just because it's interesting to be able to set that up. But I'm also going to show you like the physical device that you could buy at Radio Shack called a capacitor that you can plug into a circuit. Most of them tend to look like little tiny soda cans. They're shaped like tiny soda cans, but with two wires sticking out the sides. For most of those real-life capacitors, because they're so small, because they need to be able to fit in circuits, they tend to have very, very small distances between their two plates. I mean, you can only have so much distance if you need to squeeze the entire component into something the size of a pencil eraser. So most real capacitors will have very small distances between their two plates. But you could hypothetically build these things as big as you wanted to. There, I think, exists some capacitors the size of cars, and that's because since the capacitors can hold charge and hold energy, some systems use them like batteries. Some systems use capacitors as batteries. And so the physically bigger the capacitor is, the more energy it's able to hold on to for a longer period of time. So, that is what physically constructs a capacitor. Again, referring back to the physical nature and then how those variables affect its overall effectiveness within a circuit. With that in mind, let's actually calculate what the capacitance of this capacitor should be. We know how far apart the plates are. We know the area of the plates. We can calculate what the capacitance of this capacitor should be. So, the formula from the other slide, just to review again. Capacitance equals the permittivity constant, which is always this number, never have to memorize it, times area of the plates divided by the distance between the plates. So, C equals sigma times A divided by D. We're solving for C. Our sigma, our permittivity constant, is always going to be 8.85 times 10 to the negative 12th, so that's a freebie. Next, we need to plug in the area of the plates. We're given that the plates have an area of 200 millimeters squared. The formula does want meters and meters squared as per usual for this class, for physics class at this school, which means we are going to need to convert millimeters squared into meters squared. And so that's why instead of 200, I've written 200 times 10 to the negative 6th in here. It's times 10 to the negative 6th because you have to do the millimeters to meters conversion twice because it's squared. This is a very small squared area, so it's not going to be many meters. Like, millimeters squared is super teeny tiny, so it's not going to be many meters squared. We're expecting a small number for the area here. Similarly, we need to convert the 8.6 millimeters also into meters, but that's not meters squared. That is not millimeters squared, it's just millimeters. So we only have to do the conversion once for that one. But that's all of the variables. It's a lot of very small numbers being factored in here together. And as a result, our end total capacitance will also be a pretty small number. 2.06 times 10 to the negative 13th farads. Most real-life capacitors that, again, you could buy at Radio Shack. Is Radio Shack still open? It's the only place I know where you could historically just buy electrical components. Most commercially available capacitors will be in the microfarad range, which would be like times 10 to the negative 6th. So this is really small as capacitors go. We've built a very, very tiny capacitor here. But we have its capacitance, 2.06 times 10 to the negative 13th farads. This tells us like how good it is compared to other capacitors that can exist. And once we've calculated that capacitance, if we were to plug it into a circuit with a 1.5 volt battery, as is shown in the diagram here, the image here shows a D cell or a C cell battery. One of those two is 1.5 volts. So that is the voltage accurate for this shape of battery. We tend to only, like AAA batteries, AA batteries, C and D cell batteries, we tend not to describe in terms of their voltage because we only really talk about 9 volts that way. But 1.5 volts is the voltage of a battery that's this particular size, which will come up as we start doing labs using these size batteries. Sorry, that was an aside. If you hooked up our new capacitor to this particular 1.5 volt battery, it would be able to hold and store a certain amount of charge within itself. So, the formula that tells us that is capacitance equals stored charge divided by voltage. So, that's the second of our two capacitance formulas. We just found our capacitance, so 2.06 times 10 to the negative 13th equals Q divided by 1.5. 1.5 is our battery voltage. We can solve for the amount of charge that can be stored in this particular capacitor as it's in this particular circuit. We would get 3.09 times 10 to the negative 13th coulombs of charge. So, last little concept question asked here. Based on the formula, what effect would doubling the surface area of the plates have? Similarly, what effect would doubling the distance between the plates have? Looking at the formula, capacitance equals surface permittivity times surface area divided by distance. If you were to double the surface area, you would double the capacitance. That would double the amount of charge that it could hold. If you double the distance between the plates, then you're not multiplying by 2, you're putting 2 on the bottom and you're dividing by it. So doubling the distance between the plates would end up cutting your overall capacitance in half. And therefore, you'd be cutting the amount of charge you could hold on to in half. Which is what I attempted to show right here. Double the area, double the capacitance, double the distance, you have the capacitance. Oh, excuse me. Sorry. And that is all the information describing the physical construction of a capacitor and how they respond to voltage in a circuit. There's a lot of vocab words going around today, and I think my throat is tired of talking right now. I think we got through everything that I absolutely wanted to make sure we mentioned today. So I'll turn things to you for a second. Does anyone have any at all questions, concerns, confusion, needs, etc. about any of the information from today or yesterday? All right. Well, I think I got through everything I wanted to do today. There's one more concept that we're going to touch on as a part of this chapter, as a part of capacitance. And that's going to be how capacitors work together within a circuit. But since that's all one kind of big interconnected lesson, I think we'll just save all of that for tomorrow. I want to make sure to get through all of that tomorrow so that we can be ready to utilize it in lab this Thursday, because we're coming up on the part of the course where we're actually going to start building circuits, and we're going to first build some circuits. Well, I need to run through my list of labs actually, but one of the things we're scheduled to do is build circuits out of capacitors and check how they function together. Tomorrow we're going to be looking at the math for that so that we'll then be able to use it in lab on Thursday. Before we break, I actually want to quickly draw your attention to one more formula that's presently at the end of the notes. So I'm skipping a few slides here. This is at the end of the notes. What I want you to do is, as always, be working on the homework. This particular formula here is useful. It's at the end of the notes. I wanted to make sure to tell you where it was in case you needed to find it later. This formula here tells you not the amount of charge stored in a capacitor, but the amount of energy that's stored in a capacitor. Again, capacitors can kind of be used as batteries. You can store energy in them to discharge and use again later. And so here we have the energy stored in a capacitor. Potential energy tells you it's stored. Cap tells you that it's in a capacitor. And there's 3 different ways that you can calculate it based on what variables you happen to know. For example, if you know the charge in the capacitor and the voltage across the capacitor, you can use this version. If you know its capacitance and the voltage across it, you can use this version. Or if you know its charge and its capacitance, you can use this version. So depending on what 2 of those 3 things you know, there's a different version of the formula that you can use to calculate the energy stored within the capacitor, in addition to the charge currently stored within the capacitor. So, useful formula, wanted to point it out. So, if there's no questions, needs, concerns at this particular time, then I'll call our usual daily break here. I'll be in this room until noon. If you jump back in with questions, be working on your homework. Let me know what you need as you're working on it and as questions pile up. Tomorrow we'll look at capacitors and circuits. Thursday we'll have lab. Friday we will wrap up chapter 16 and give everyone time to work on your homework before we start chapter 17 next week. Let me know what you need. Jump back in here with any questions, issues you have. But if I don't see you again today, then I will see you tomorrow.